So in this question number 9, this is actually part of the all syllabus. They used to have a section B on biochemistry. All of these are no longer relevant for this 2022 syllabus under the Cambridge International. In fact, it has been out since the 2016 revamp of the syllabus actually. So there's quite a lot of biochemistry in here. Used to be favorite among biology students. Obviously, these are no longer the favorites of people who don't do biology. And these are chemistry exams. So it's a very good thing that Cambridge has, shifted the focus of the chemistry exam to more chemistry and less biology. Anyway, there is a bit of NMR stuff in that particular question, and I thought it's actually quite nice to go through these particular questions. So this NMR spectrum of cysteine, we know that cysteine is an amino acid. So what happened is you got that NH2 and the CO2H. That is your basic amino group. And then you have the acidic carboxylic acid group. And these are still in the amino acids and protein chemistry in the current syllabus. And you have an R group and a H. This is how a general amino acid looks like. Your R group here is CH2SH. So I'm just going to put in the CH2SH. Now after we shake a solution of cysteine, so that means cysteine dissolved in water, with a few drops of D2O. We know the purpose of D2O is to do a fast exchange. This is as stated in the syllabus, obviously. Fast exchange of, I better separate out my fast and the exchange so that it looks better. Fast exchange of labile. Labile means easily come off. So which ones are labile protons? OH and also NH are labile protons. You have NH there. You also have OH on the carboxylic acid end. So now your spectrum only shows 2 adsorptions because this and this will be gone by now as they are labile protons. So what happened then is what you see? Well, you will see the SH protons. And hang on, the NMR spectrum shows only 2 adsorptions. I wonder, why does it say only 2 absorptions? We know this and these are labile. Now there are 2 absorptions. So we have we have SH, we have CH2 and the H. I wonder if the SH is also labile protons because you started from 5 absorptions. Now you have lost 3 absorption because you only have 2 absorption now. Well, the only thing that doesn't make sense is the SH here, but let's see what's happening. If I have this very clear stuff, which is, let's say, A and B, if I add A, I will have 2 neighboring protons, so A will see a triplet because 2 neighboring protons, so therefore 2 plus 1 equal to 3 lines, so that is your triplet. Identify 2 types of proton responsible, so looks like A has to be this distinct adsorption E here, and F is a doublet. If I am here, assuming that SH, probably this one behave like OH, assuming, I am not entirely sure, but it seems like if when you are here you only see 1 neighboring protons because you don't couple to proton on OH. It seems like you also don't couple to the protons on the SH. So what happened there is you will have 1 neighboring protons because you only see these neighboring protons that you couple to. Coupling is this concept in NMR, which you don't do so much in A-level chemistry, but that is the origin of this splitting. So when it couples to these 1 neighboring protons, you will see 1 plus 1, that's your n plus 1 rule, and you will see 2 lines, and 2 lines represent a doublet. They are of equal intensity, 1:1, and this 1:2:1 intensity for this triplet. So it looks like that must be B there, and the SH is just another labile proton, just like NH and OH, although this is not technically in the syllabus, but the information very clearly shows that this must be labile as well. That's why you could do a fast exchange with D2O. So what are the 2 types of protons there? So A is going to be CH, CH2SH. This is where you are, and where you are, I'm going to underline it so that it is very clear I'm talking about where I am. And this is very common trick in more advanced NMR study, and usually this is what I teach my students. You must show the neighbor. If you don't show the neighbor, how would you know how many neighboring protons there are? Okay. Now to the other one, F is going to be this signal here. So again, we have CH, CH2SH. but now we are here with the 2 protons. We see 1 neighboring protons. We don't couple to that. Therefore, we see 1 plus 1, which is 2 lines and the doublet there. State and explain. So here there are 2 bits to it. You see there are 2 lines. Do not just explain, do not just state, but state and also explain. For this signal or absorption at E, we see a triplet. This triplet is a 1 to 1 to 1 intensity. 1:2:1 intensity. And because this CH2SH, the one I underlined, will cease, or it has 2 neighboring protons. So we talk about 2 neighboring protons. Therefore, 2 plus 1 equal to 3 lines, and 3 line is a triplet of 1:2:1 intensity. I'm pretty sure you won't get penalized without the intensity ratio, but I'm just telling you that's part of the Pascal triangle, which you have done in mathematics binomial expansion. Where was I? That was actually part of the previous question. There was the explanation. So now to the red color one. There is the doublet there. So we get a doublet for the other absorption because, well, the part 2 is the reason. So now I underline the CH2 of the SH, and then it sees, well, it has 1 neighboring protons. And when you have 1 neighboring proton, that is a singular, by the way. Therefore, you get 1 plus 1. The n is number of neighboring protons plus 1. Then you get 2 lines, and 2 lines will all be of equal intensity. That is your doublet of 1:1 intensity ratio. And that's the end of the NMR questions of these whole biochemistry questions. Very interesting question on NMR, especially on the fast exchange in the presence of D2O, where this labile proton disappear. But it turns out that this is also labile. It behaves just like OH or NH, although it's not really straightforward, like in your syllabus stated clearly, but you can very clearly indicate what is happening here based on the absorption as shown here.